This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 04. Pure Substances and Steam Tables. The skill that separates fast exam performers from slow. Navigating the tables correctly the first time. Phase identification, which table to enter, and interpolation between rows. Every Rankine and open system steam problem starts here. Here's the problem. Water at 1 megapascal and 280 Celsius. Find the phase, specific enthalpy, and entropy. 280 isn't a tabulated row. The table lists 250 and 300, so you'll interpolate. Classic exam pattern, a temperature picked between rows to test your interpolation. By the end, you'll do it in about 90 seconds. A pure substance has uniform composition. Water, R134A, air under non-reacting conditions. Any two independent intensive properties pin the state. The rest are tabulated. The steam tables are that tabulated equation of state for water. You don't rederive, you read. The skill we're building is speed. Navigating them quickly beats any formula memorization. 3 regions on the PT diagram. The yellow saturation curve is where liquid and vapor coexist. States on it use the saturation tables, where quality matters. Above it is compressed liquid, below it superheated vapor. Today's state at 1 megapascal, 280 Celsius, sits below and right of the curve. So, superheated. The shortcut, is T higher than T sat at that P? If yes, superheated. 6 steam tables total. 2 sat by temperature indexed by T, 2 sat by pressure indexed by P, same data, sorted differently. 2 superheated tables cover everything above saturation, IP or SI, pick one. There's no compressed liquid table. Approximate from saturated liquid values at the given temperature. V roughly VF, U roughly UF, and for H, a small pressure correction. Typically 1%. Drop it unless pressure is very high. Phase identification decision tree. Step 1. Enter a saturation table to find the partner. At 1 megapascal, Tsat is 179.9 Celsius. Step 2. Compare. 280 is hotter, so superheated. Equivalently, 1 megapascal is below Psat at 280, which is 6.4 megapascals. Same answer. Step 3. Enter the superheated table. Interpolation. If the row you need isn't tabulated, linearly interpolate between the two nearest values. YA plus the slope times the distance from the lower bracket. 2 rules. 1. Interpolate enthalpy and entropy together at the same fractional distance, since they share one state. Don't pull H and S from different rows. 2. For double interpolation, when both P and T fall between rows, nest the one-dimensional interpolations, P first at both T bounds, then T at the intermediate P. Handbook quick reference. For today's problem, first check Tsat at 1 megapascal, then enter the 1 megapascal block of the superheated table. 280 Celsius falls between the 250 and 300 rows. The fractional distance is 280 minus 250 over 300 minus 250, 0.6. Compute it once, reuse it for every interpolated property. Solve. Step 1. Phase check. At 1 megapascal, Tsat is 179.9 Celsius. Given 280 is higher, so the state is superheated. Enter the SI superheated table. Step 2. Locate the bracket. At the 1 megapascal block, the tabulated temperatures near 280 are 250 and 300. 280 sits 6/10 of the way between them. Write that fractional distance down, 0.6. You'll use it for both H and S. Step 3. Interpolate. Apply the linear formula at fractional distance 0.6 between the 250 and 300 rows. Enthalpy lands at 3008.2, entropy at 7.0443. 3 operations per property, no intermediates to lose track of. Final answers. Phase superheated, enthalpy 3008, entropy 7.04. Sanity check. Both fall between the 250 and 300 degree values, as they must. If an interpolation result lands outside the bracket, you made an arithmetic mistake. Redo. Linear interpolation can't produce values outside its input range. Bonus: compressed liquid shortcut. Same 1 megapascal, but at 100 Celsius. T is below Tsat, so compressed liquid. No dedicated table, so approximate from saturated liquid values at 100 degrees. V roughly VF, U roughly UF, S roughly SF. For H, a small pressure correction. VF times P minus Psat works out to about a 0.2% effect. For pump work and Rankine state 2, you usually drop it and just use HF at the given T. Traps: 5 ways steam table problems lose points. 1. Always phase check first. The wrong table gives garbage. 2. Interpolate H and S together at the same fractional distance. They share one state. 3. Use the right table for the given variable. Pressure given, sat by P. Temperature given, sat by T. 4. Double interpolation. If both P and T fall between rows, nest them. T at the lower pressure, T at the higher. Then interpolate in pressure, not a simple average. 5. Don't mix unit systems. Kilopascals aren't PSIA, Kelvin aren't Rankine. Quick recall summary. Given P and T, phase check against the saturation partner. Superheated, saturated, or compressed liquid each have their table. Inside the dome, apply quality weighting. For interpolation, compute the fractional distance once and apply it to every property. Practice until you go from phase check to interpolated answer in under 90 seconds. Next up, Topic 5. The ideal gas law and mixtures. For gases far from saturation, we skip the steam tables and use PV equals mRT. We'll cover the ideal gas equations, specific heat relations, Dalton's law, and when the assumption breaks down. Before that video, for 1 megapascal at 500 Celsius, a tabulated row, confirm H is 3,479 and S is 7.76. PEPrepengine.com/beta. The steam table cheat sheet, the worked problem PDF, and a 5-question quiz are attached. If the course helps you, subscribe.
The full study guide with every equation and common exam trap is free at PEPrepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.